In this section, we will introduce and discuss the new notion of a limit of a function. That, of course, you are familiar with already from regular calculus. And before making things rigorous, let me just remind you of a few examples. Maybe first graphically, and then we'll compute a couple of limits. Graphically, let's look at the following function. Okay, so f of x is going to look like this. Then maybe like that. A vertical asymptote. And then maybe a horizontal asymptote. Something like this. And let's label a few points here. So this will be A, B, C, and maybe so let's call this P, this one is Q, and this number is R. And I want to consider the following limits. So let's look at the point A first. Now, forget about the advanced calculus and just try to remember what we knew about limits from before. I want to compute the limit as x goes to A from the right of f of x, from the left first. Limit as x goes to A now from the right. And then the limit x goes to A of f of x. Now, clearly in this case, the function has a jump at A, right? If x goes to A from the right, so now what does a limit mean in this case? It means that as x gets closer and closer to A and stays to the left of A, then the values of f of x will, or will not, get close to some number. And in this case, clearly they will get close to some number, because if I'm taking a smaller and smaller region around A and staying to the left of A, then the values of the function are going to get closer and closer to the point, to the value P. So this limit is NP. What about the limit from the right? Well, similar thing is going to happen. So now we'll look at what happens to the values of a function as x stays to the right of A and it gets closer and closer to A. So then examining the graph, we see that values of f are going to get closer and closer to Q. So that means that this limit from the right is Q. And now if we simply take x close to a, then on the right, the values of f are going to be close to q. On the left, they're close to p, so there is no common value to which f of x is going to be close if x is near a. So that means that this limit does not exist. And you might recall from calculus again that the limit of the function as x goes to a exists if and only if the limit from the right exists, limit from the left exists, and those limits are the same. All right, so part 2, let's look at point B. So what do we have here? Same questions. Limit x goes to a minus of f of x. In this case, if x gets close to b from the left, then f of x is going to get close to r. So this would be r. Limit x goes to a plus of f of x. Same deal, right? Because if x is close to b actually from either side, then if we look at values of f of x, they get closer and closer to r. So this limit is equal to r, limit from the right. And likewise, the limit x goes to a of f of x is equal to r, because limit from the right and limit from the left are the same. Now, what about C? So number 3. We take a limit x goes to a minus of f of x. What do we get? We get that, not a minus, in fact, sorry, it was not a here either. B minus, B plus, and B. And in this case, it's C minus. So x gets close to C from the left. As x gets closer and closer to C from the left, coming from the left, then what happens to f of x? Values of f of x go to, they become larger and larger. So in this case, we'll say that the limit is equal to infinity. Likewise, the limit x goes to C from the right of f of x is also infinity, right? Because as x approaches C from the right, the graph goes to infinity, so this limit is infinity. And then the overall limit from the right, limit from the left, they are the same, so we say that the limit exists. The limit of f of x exists and is equal to plus infinity. Let me add one more point here. Let's say D, and I'm going to make a small hole here. And put a circle and place a value at D at this point. So roughly speaking, the circle is going to be located at Q probably. So let's do it this way. The circle is at Q, and the value of the function now is at P. So I generated a hole. Same question. Number 4. Limit x goes to d plus f of x. Limit x goes to d, well, let's do d minus first. D minus d plus f of x, and the limit x goes to d of f of x. What are those? Well, so as x goes to d, now it goes to d from the left. What do we see? We see that the values of the function are decreasing and getting closer and closer to q, right? So that means that this limit is equal to q. What about coming from the right? Same thing, except that if you go to d from the right, then values of the function are getting bigger, and they're approaching q again. They're approaching this hole that I drilled inside the graph, so this is q. So limit from the right and limit from the left are both the same, and so the limit of f of x at d exists and is equal to q. This is just to emphasize that the limit may exist at a point, but the function still has a jump at that point, right? So the value of the point I'm trying to make here is that the value of the function at the point in principle has nothing to do with the limit of the function at the same point, right? Because in this case, the behavior of the function from the right and the left, as x gets closer to d, indicates that the values of the function will get closer and closer to q, but the value of the function at d is equal to p. Okay, so we have that example, and now the last one here, example number 5. Let's take a limit x goes to infinity of f of x. Is that something that is defined in this case? Well, we have a horizontal asymptote at p, so that means that as x gets bigger and bigger, f of x is going to get closer and closer to p, so the limit is equal p. One other thing that I would like to point out here. If I look at the graph of my function at a, b, c, and d, what I see is that at a, clearly the function is jumping, so it's not continuous. At b, it is continuous. At c is not continuous. It's not continuous because the graph goes to infinity from both sides, from both directions. And at d, again, the graph is discontinuous because when you pass through d, you have to jump down from q to p and then back up. So you might then recall the definition of continuity of functions that was introduced in Calc 1, and that was that basically the behavior of the function close to the point it must be exactly the same as the behavior of a function at the point, meaning that the limit of the function at a given point must be equal to the value of the function at that point. That certainly is true at b, but it's true nowhere else. Not true at d, not true at c, not true at a. So let's write this as a note here. f is continuous at a at b because limit x goes to b of f of x is equal to f of b, and f is not continuous at a, c, d. So moral of the story from this example is the following. That I have a whole bunch of different limits that I can discuss, right? Limits from the right, limits from the left, limits from both sides, limits as x goes to infinity. And the value of the limit can be either a finite number like p, q, or r, but it also can be infinity, and in principle it can be minus infinity. So in the definition of a limit that we want to give, we don't want to give different definitions to different limits, because then we're going to be drowned in definitions. Furthermore, the properties of limits from a right, from a left, or all limits, right, they all should be basically the same, like a limit of a constant time of function from any side must be equal to the constant times the limit of the function, etc. So it would then make sense to try to give a general definition of a limit that will encompass all possible limits that we're listing here. That is number one. And number two, the notion of continuity that we already introduced should be related to the notion of a limit, right? Because the existence of a limit of a function at a point must be, if that limit is equal to the value of the function, ensures the continuity of the function. So whatever we're going to do about limits somehow must be similar to what we did when we discussed continuity of functions. All right, and so this would be a good point to give that definition. Now, remember that the way I define continuity, I define it in two different ways. Now, the way number one involved sequences. And basically, what did we say there? We said that the function is going to be continuous at the point x if, when I take a limit, when I take a sequence on x-axis that converges to x, then the sequence of corresponding values of the function should converge to f of x. So let's try to do the same thing here. Let me draw another graph. So, definition of continuity. Not of continuity, of the limit. Again, should be related to the definition of continuity. So let's do a picture. Say I have a function. I have some point A on x-axis. So maybe my function looks like this. And I want to see if this function has a limit, let's say from the right. From the right is fine. How do I know if it has a limit from the right? Clearly, in this case, as x gets closer to a from the right, the values of f of x will approach this number that I'm going to call L. Now, what does it mean? Why is this true? Let's try to use sequences. So let's take a sequence of xn's that converges to a, and because I'm talking about the limit from the right, then I want my sequence to be completely to the right of a. So let's suppose xn is such that the limit n goes to infinity of xn is equal to a. And not only that, xn, because again I'm talking about the limit from the right, I want xn to stay larger than a. What happens to the corresponding values of f of x? So f of x1, f of x2, x3, x4, and so on. What happens to these values? Clearly, they get closer to L, right? So then I can see from here that the limit n goes to infinity f of xn is L. So if I pick any sequence xn like this, so xn's are to the right of a, and xn's converge to a as n goes to infinity, for all sequences like that, in this particular case, this will be true, that the limit as n goes to infinity of fxn must be equal to L. And so that means, right, that the limit of my function as x goes to a from the right, as x goes to a from the right is equal to L, right? So from here, I'm going to conclude that the limit x goes to a from the right, this is L. Notice one thing, that my function is not defined at a, but really this has no bearing on the fact that the limit exists and equal to L, because when I compute the limit, I'm actually concerned only with values of f of x near a, not at a. Okay, likewise, we can do the similar thing, but if I now want to consider a limit from the right, what would I do? I'll take another sequence. Let's call it x bar 1, x bar 2, etc. And I look at values of f along that sequence. What happens to them? As x1 bar goes to a, then f of x1 bar, as xn bar goes to a, what happens to f of xn bar? The values are getting closer and closer to L again. So that means that if I'm taking xn such that the limit n goes to infinity of xn is a, and now xn is less than a for all n natural, it will follow that the limit as n goes to infinity f of xn bar, this also is equal to L. Right? And from here it's clear, it doesn't matter which sequence below a and convergent to a I choose, values of f along that sequence would always converge to L. And so then, not surprisingly, this is the same thing as saying that the limit x goes to a minus of f of x, that should be L. And now finally, I don't have too much space here, but in this case, actually, if I take any, I don't have much space on the picture, so I'm just going to say it in words. If I take any sequence that contains points to the right and to the left of A on the x-axis, and that sequence converges to A, right, and it's clear from this picture that the values of f of xn along that sequence would also converge to A. So that means that the limit of my function as x approaches A actually exists and is equal to L. So let's write it down as well, maybe in a different color. Let's say xn is such that the limit n goes to infinity of xn is equal to A, right? And it doesn't matter where xn is located. As long as xn converges to A from the picture, it's clear that the limit n goes to infinity f of xn is still equal to L. What does that mean? It means that the limit x goes to A of f of x is equal to L. Okay, so then as a motivation for the definition, what exactly should I do? So what is similar between these examples and what is different? Similar is I take a sequence that converges to A, and then f along that sequence will, and I'm missing bars here, x and bar, x and bar, x and bar. So in all examples, I have sequence, I take a sequence which converges to A, and along any sequence that converges to A, values of f will converge to the same number L. The difference between these is as where I take my sequence, right? When I look at the sequence coming from the left, I'm taking xn less than A. If I look at the sequence where x comes from the right, xn must be bigger than A. If I take any sequence that converges to A, then I don't place any restriction or on where I can choose my my xn. So this will motivate the following definition, which will be common for all of these situations and more. A limit as as x goes to as of f of x is equal to L if for any sequence xn such that xn is contained inside S for all n in N, and a limit n goes to infinity of xn is equal to A, we have the limit n goes to infinity f of xn equal to L. Right, so that is going to be our definition. Notice this is exactly like what you have in the picture. If I'm looking at the limit from the right, I'm taking a sequence xn. What is my set S in this case? In this case, set S is going to be the set of all numbers that lie to the right of A. When I take a limit from the left, again, where do I take my sequence? I take my sequence from all points to the left of A. So then S is going to be a set which consists of all points that are less than A. And in principle, where my function is defined, because otherwise I will not be able to compute f of xn. Now, here, A and L both can be finite numbers or plus infinity and minus infinity. So let me see if I can squeeze this in here. So here A and L are either in R or equal to plus or minus infinity. So that means that my definition actually is going to encompass both finite and infinite limits, as well as limits at plus and minus infinity. All right, so let's try to do a couple of examples. In fact, let's summarize what we just said, because in a sense we already did a couple of examples. So let's just note a few things. For a limit x goes to a plus of f of x, S, as I said, should be the set of all points to the right of A. And in fact, because we're only considering sequences that converge to A, then in fact it is sufficient to make S to be a short interval to the right of A. So I can take S to be an open interval AB for some B greater than A. For limit x goes to a minus of f of x, in the same way, I should take an interval from some B to A, where B is now less than A. For the limit x goes to A of f of x, what do I need to do? I need to take some interval which contains A, and it can have points both on the right and on the left of A. But it cannot contain A itself. So S is going to be some B, C minus point A. And this is for some, let's see, B less than A less than C. So I take an interval from B to C, I puncture it where A is, and then I can take X at all points inside this punctured, I can take my sequence, select my sequence from all points in this punctured interval from B to C. Okay, what are the other kinds of limits? We can have an infinite limit. So for a limit, x goes to a f of x equal to infinity, what do? Well, it's the same thing, right? In fact, we don't really even need to write this as a separate case, because for the infinite limit, I would still take the same punctured interval as in the previous case, except that then along any sequence xn that converges to a, the values of f of xn must go to infinity. So instead, let's look at this guy. X goes to infinity, and this limit might be equal to whatever. So what is the appropriate choice of s in this case? Well, in this case, then my sequences xn must go to plus infinity, so s should be some interval from some point a to infinity, right? And this is for just some number, right? And then finally, for the limit x goes to minus infinity of f of x, s should be an interval from minus infinity to a for some real a. Right, so the distinction between different kinds of limits again comes down to just selecting different choice of a set S from which you are going to draw your sequences xn. Okay, so let's do now more examples. Can we compute the limit x goes to 2 of x squared? Well, what do I need to do? So if this is x goes to 2, that means that as my set from which I'm going to select sequences xn, I should select any interval that contains the point 2, right? So choose any sequence xn such that the limit n goes to infinity of xn is equal to 2, right? Again, I'm not placing any restrictions on where xn can be, right? It can be to the right, to the left, as long as it's close to 2. Then, what will be the limit n goes to infinity of xn squared? Properties of the limits of limits of sequences, right? Tells me that this must be the limit n goes to infinity of xn quantity squared, which is equal to what? Xn goes to 2, so limit of xn is equal to 2, so this is 4. And this is true for any sequence, right? So therefore, limit x goes to 2 of x squared is going to be equal to 4. Let me move this forward to save some space. right? So then from a definition of the limit of a function, the limit of x squared must be equal to 4. Let's do another one. Limit x goes to 1 minus, I don't know, 1 over x squared. What do we do here? We're going to choose any sequence xn such that, so in this case this is a limit from the left actually. If I'm taking a limit from the left, then I need to choose a sequence from where? I have to choose it from a set of x's which are less than 1 in size. So such that xn is less than 1 for all n, and the limit as n goes to infinity of xn is equal to 1. And then I need to take a limit as n goes to infinity of f of xn. So in this case, it's 1 over xn squared. And again, properties of limits of sequences tell me that this should be 1 over the limit as n goes to infinity of xn square, right? Because limit of the reciprocal is equal to reciprocal of the limit as long as the limit itself is not equal to 0, which is true in this case because limit of xn is 1, and the limit of xn square is square of the limit of xn. So this is equal to 1 over 1 square, so equal to 1. It doesn't even matter what sequence xn I'm choosing, as long as it goes to 1, that's enough. And so that means that now from the definition of a limit of a continuous function, this limit as x goes to 1 minus 1 over x squared is equal to 1. One more example. Limit x goes to 0 plus of the same function, 1 over x squared. Okay, so do the same thing. Choose any sequence xn such that the limit n goes to infinity of xn is equal to 0, and because we're converging to 0 from the right, I want xn bigger than 0 for all n in n, right? So then what is the limit n goes to infinity of 1 over xn squared? And here you might remember, so first thing, xn goes to 0, that means that the denominator goes to 0, so properties of limits you cannot use. But at some point we proved the theorem about sequences that go to 0 and stay positive, right? Xn in this case is a positive number going to 0. Xn squared, in fact, then is a positive number that goes to 0, again, by properties of limits. we had a theorem that stated that when a sequence goes to 0, then 1 over that sequence goes to 0 and remains positive. Then 1 over that sequence must go to infinity, and vice versa, in fact. So in this case, I have a sequence of positive numbers that goes to 0. So limit of 1 over that sequence must be infinity. By that theorem, I don't remember what you should be able to find it. Limit of a sequence of a positive sequence is 0 means that the limit of 1 over that sequence is going to be infinity. And so this is true for any sequence xn that satisfy our conditions that it goes to 0 and remains positive. And so that means that the limit that I'm computing, x goes to 0 plus 1 over x squared, then this limit must be plus infinity. Again, this is a consequence of a definition of the limit. Last example here, limit x goes to infinity of, let's say, 1 over x plus 2. Now, what is that? So in this case, what is my set S? I consider x going to infinity, so I should be able to select sequences that go to infinity. So I'm going to choose any sequence xn such that the limit n goes to infinity of xn is equal to plus infinity, right? I should be able to always select a sequence like that. Along that sequence, right, in fact, my function 1 over x plus 2 is always defined. So as I said, S, for instance, I can take all x's greater than 0. Okay, so and then in this case, then what is a limit as n goes to infinity of 1 over xn plus 2? Well, so xn again is a positive sequence that goes to infinity. Then xn plus 2 is also a sequence that goes to positive infinity, right? Because if xn becomes arbitrarily large, so does xn plus 2. And then the same theorem that I mentioned in a previous example, but going in the opposite direction. If I have a sequence of positive numbers that goes to plus infinity, then a limit of 1 over that sequence must be 0. And this is true for any sequence like this that goes to plus infinity. And so therefore, by definition of the limit as x goes to infinity of 1 over x plus 2, this limit should be 0. Okay. One observation then. So note. F is continuous at A per our definition that we gave last week if for any sequence xn such that the limit n goes to infinity of xn is equal to A, it follows that the limit n goes to infinity of f of xn should be equal to f of a, right? That was a sequential definition of a limit, of continuity. Well, but let's look at this more carefully. What it says is that for any sequence xn, such that the limit of xn equal to a, the limit of f of xn is equal to f of a. But that matches perfectly our definition of a limit that we just gave, right? In this case, I'm not restricting xn to be to the right or to the left of a. So that means that I'm talking about a limit as x goes to a. So this is equivalent to saying that f is continuous at a if the limit x goes to a of f of x is equal to f of a, right? So the limit definition, the continuity definition becomes slightly shorter because the sequential piece now goes into the definition of a limit, right? Again, if for any sequence xn such that the limit of xn goes to a, it follows that the limit of f of xn is equal to f of a. That's the definition of a limit that we just gave. Limit of the function as x goes to a must be equal to f of a. And so that now allows us to compute limits, in particular for functions that are continuous, right? So if, for instance, I go back to my, let's say, first example here, well, function x squared is continuous. If it is continuous, then it's continuous everywhere. In particular, it's continuous at 2. So then if I want to compute the limit as x goes to 2 of x squared, I just can plug in x equal to 2, and then I'm done, right? So if we do example like this, limit x goes to, let's say, 5 of x cubed plus 1 to the power 1/2. I look at this function, x cubed plus 1 to the power 1/2. It's continuous on its domain, so let's assume that it's continuous on its domain, although we can prove it already by using things that are proved in Advanced Calc 1. But let's assume for a moment it is continuous, that we know it is continuous. So then what is the limit? The limit is just the value of the function 5. So this would be 5 cubed plus 1 to the power 1/2. So square root of 126. Right, so the computation of a limit is immediate. If I take a limit x goes to 1 of e to the power 2x, likewise, exponential function. Again, we didn't prove anything about exponential function, but if you prove that it is continuous, then this immediately becomes e squared. So computation of limits for continuous functions is a piece of cake. What about another example, which is going to be very relevant when we're computing derivatives? Let's say I want to figure out limit as x goes to 3 of x squared minus 9 divided by x minus 3. Can I use my continuous function idea to figure out this limit? Clearly not, right? Because the function x squared minus 9 over x minus 3 is not defined at 3, right? So I cannot just plug in 3 and say what the limit is. And likewise, I cannot plug in 3, say, okay, my function is undefined at 3, so therefore the limit does not exist. You have to be very careful here, because if we go back to this picture, right? So here the function is not defined at a, but certainly the limit exists at a. So what would you do for an example like this? Well, again, you might remember that this is an indeterminate form 0 over 0. So what you need to do is take advantage of the fact that you're actually not working with x equal to 3, but you're working with x's that are close to 3. So you can simplify or factor out the top. And because x is not equal to 3, x minus 3 can be cancelled. So then the limit that we're computing must be the same as the limit when x goes to 3 of x plus 3. And x plus 3 now is a continuous function. So its limit is equal to 6.